Welcome back. I have one more rational function that I would like to graph to give you an idea of the various types of graphs that you can come up with in this section. So this function, we will go through all the same steps, find the domain, the intercepts, the asymptotes, and then graph using as many additional points as necessary. So to begin with, we will look at the domain. Now notice we can write this function in factored form in the numerator as x plus 4, x minus 1, all over x minus 4. Now it looked like things might cancel, but in fact they don't. This function is as reduced as it will get. So we can jump straight to looking at the denominator. When is x minus 4 equal to 0, so we can avoid that x value? Well, if x is 4, that's a problem. So we'll say that the domain excludes 4. So negative infinity up to 4. Skip 4 and continue from there. And now we're good to look at the intercepts. So I think I'll look at the y-intercept first. Now which function or which version of this function you use is entirely up to you at this point. So to find our y-intercept, we want to let x be 0 and see what happens. Now I think I'll go with the original form that the equation came in. So I'll plug 0 in, 0 squared plus 3 times 0 minus 4 over 0 minus 4, and then everything with a 0 is going to become non-existent, and I'll just end up with negative 4 over negative 4 for a grand total of 1. So our y-intercept is located at 0, 1. And now we can look at our x-intercepts. So if we are finding our y-intercept, we let x be 0. If we are finding our x-intercept, we'll let y be 0. In other words, we'll set our function to 0. Alright, so now I have a rational equation, and a fairly nice one, to solve. I can do so by multiplying both sides by x minus 4. And that will clear out my fractions. And on the left-hand side, I have x minus 4 times 0, and that is trivially 0. And our right-hand side is just going to give us the numerator. So in reality, we only actually have to solve this nice quadratic equation. And we already saw that the numerator factors as x plus 4, x minus 1. So it seems x equals negative 4 and x equals positive 1. So those give us our x-intercepts, negative 4, 0, and 1, 0. So we have 2 in this case. And we can move on to the asymptotes. I'll go for the vertical asymptote first. That's the simpler one to deal with. I'll take my reduced form of the function. Remember, this was as reduced as our function got. If we factored it, we saw that nothing cancels. So I can just grab that denominator and set it equal to 0. When is x minus 4 equal to 0? Well, we talked about that when we looked at the domain. So that's going to happen when x equals 4. Alright, so again, notice the difference. The vertical asymptote, this vertical line at x equals 4, is occurring at the one x value that is not in the domain of our function. So on to the horizontal or oblique asymptote. Now we'll look at our function, and I'm not sure which one we're dealing with here yet. So horizontal or oblique, that's the decision, if there is an asymptote to find. So I'll look at the original form of my function, x squared over x. So I'm just looking at the leading terms, the highest powers of x, and I notice the numerator is 1 larger than the denominator. So m is 1 greater than n, and this implies that we have an oblique oblique asymptote. And now to find it, we will divide our numerator polynomial x squared plus 3x minus 4 by our denominator polynomial x minus 4. We'll perform the division that this function is indicating. So I need an x, and I'll multiply my divisor by x to get x squared minus 4x. And now I will subtract that. So x squared minus x squared gives me 0, and 3x minus negative 4x, effectively 3x plus 4x, is 7x. And I'll bring down the minus 4 left over. And I'll start from the top. I'll compare the leading coefficient of what I'm looking at and the leading coefficient of my divisor. And it looks as though I need a 7. So 7x minus 28 is going to go down below, and I subtract that, getting 0x and negative 4 plus 28 for a remainder of positive 24. Now what we care about is the quotient. This quotient up top is our oblique asymptote. So y equals x plus 7, and this time around we're actually going to graph it. So the final question that we would like to answer is, does our function cross its oblique asymptote? In other words, is our function x squared plus 3x minus 4 over x minus 4, is this ever equal to its oblique asymptote, x plus 7? So again, when I check to see if our function crosses its asymptote, I set up an equation. So again, to solve this, I might multiply by the denominator to clear the fraction. And I see that I get x squared plus 3x minus 4. And if I FOIL out the right-hand side, I have x squared minus 4x plus 7x minus 28. So if I try to gather my x's on one side, I can add or subtract x squared, subtract 3x, and I end up with negative 4 equals negative 28. And that is obviously untrue, which means this is not valid, and this is not valid, so our original assumption is not valid, and it does not cross. So the only thing left to do is to plot all of the information that we have. I will throw my asymptotes up first. We have our vertical asymptote, x equals 4, and we have our slant asymptote, y equals x plus 7. So the line with a y-intercept at 7 and a slope of 1. So if I rise 1 and run 1, rise 1 and run 1, rise 1 more, run 1 more, and ultimately I smack into my vertical asymptote. Now I'll plot my y and x intercepts. Remember, my y-intercept was at 1, and I had two x-intercepts at negative 4 and positive 1. And now the image that we are seeing is going to behave something like this. Our function doesn't cross its vertical asymptote, and it certainly doesn't cross its oblique asymptote. We just discovered that. So finally, the only thing left to do, since I know what's going on to the left of my vertical asymptote, is to graph or to plot a point to the right of the vertical asymptote, or more than one point, usually would be a good idea. So if I plug something in past 4, maybe 5, my function f of x is going to square it, add 3 times 5, subtract 4, and my denominator 5 minus 4. So my denominator is just 1, my numerator is 25 minus 15 minus 4, which is 10 minus 4, 6 over 1, so we are at a height of 6. Alright, so my function is below my slant asymptote over in this area, and I know it's never able to cross it, so we are stuck below. So we have collected our information about this graph that we've gathered so far. We know our intercepts at 0, 1, 1, 0, and negative 4, 0. And we know our asymptotes occur at x equals 4, the vertical asymptote right there, and our slant asymptote of x plus 7, so if we come up to 7, and rise 1 and run 1, and rise 1 and run 1 more, and again, and again. Now I'm using open circles, because again, I don't actually include this line, it's just there for the purposes of graphing. And if I extend down in this direction, this asymptote does go on forever. So I can tell, at least to the left of my vertical asymptote, what's happening with the graph. We know it passes through each of these 3 points that we've already plotted, and we know that it doesn't cross either of these asymptotes, so it's stuck below and will eventually approach each of them in a fashion somewhat like this. Now, to know what's happening in the rest of the graph, we'll need to plot some points. So if I plug in an x value beyond x equals 4, beyond my vertical asymptote, I'll see what y value we end up with. So if x equals, say, 4.5, I'll choose a very small step. So we're just a little bit beyond 4. So my function would be 4.5 squared plus 3 times 4.5 minus 4 over 4.5 minus 4. And if I plug all of that into my calculator, I see that our y value would actually be 59.5, so very large, and most importantly, above my slant asymptote. So this lies above that slant asymptote, which means that our entire remaining piece of our function will also. So we can conclude that our graph might look something like this, and it will adhere to those asymptotes, never crossing either of them. So if you plot this function in your calculator, this is f of x equals x squared plus 3x minus 4 over x minus 4. And if you zoom out far enough, you will see a function that looks something like the solid lines that we have graphed up above. So that is how you would handle an oblique asymptote. Our function may behave in exactly the same way relative to a slant asymptote or an oblique asymptote as it would to a horizontal. We have to see if it crosses it, and if it does, we deal with that as it comes, and if it doesn't, then we know we are trapped by that asymptote.